In this chapter, we're going to look at NMR, or nuclear magnetic resonance. Now, out of all the analytical techniques you're going to come across in this course, NMR is probably the most useful to any organic chemist. If you go on and continue on into organic chemistry research, especially synthetic organic chemistry, you're probably going to use NMR on a daily basis. It's even if you're not doing NMR research, just you'll notice in this course from this chapter onwards, we're going to be relying on NMR a lot to determine what the structure of our molecules are. Okay, so NMR data is a very important piece of a puzzle when you're trying to figure out the structure of an unknown. Okay, and you'll notice that in a lot of questions we're gonna get from this chapter onwards. So what is nuclear magnetic resonance? Well, basically, we're going to look at how the nuclei of certain atoms behave in a magnetic field. All right, that's essentially what it comes down to. In this chapter, we're going to focus on carbon and hydrogen. So really in this course, in general, we're just going to primarily focus on carbon and hydrogen, which you'll find out is plenty. Since we're dealing with organic chemistry, and carbon and hydrogen are the most common elements in our organic compounds, usually the NMR of carbon and hydrogen are sufficient to figure out what you need to know about a particular molecule. Now, why is nuclear magnetic resonance so useful? Unlike other analytical techniques that just tell you what's there, NMR also tells you how the pieces are connected together. You get information about the environment that these different nuclei are in. Okay, and that tells you what's in their immediate vicinity, and then you can kind of piece together how the different parts of your molecule are connected, and therefore you can figure out the structure of the molecule, which again puts NMR way ahead of most other analytical techniques in terms of usefulness. So, how does this work? Well, first of all, we need only certain type of nuclei that are capable of interacting in our magnetic field. You need an odd number of nucleons. Now, by nucleons, I mean particles found in the nucleus, protons and neutrons. And when you have an odd number of these, this allows the nucleus to spin, so to speak. All right. Now, I mentioned earlier that we're going to primarily look at carbon and hydrogen. That's really all you need. But there are lots of nuclei that meet this requirement, right? So hydrogen 1, of course, and carbon 13 are examples of nuclei that have odd numbers of nucleons. But you can use NMR with things like nitrogen 15 or fluorine 19 or phosphorus 31. We're not going to deal with them in this course. It's kind of rare that you'll have to run an NMR on one of those. And to be honest with you, if your research leads you to needing that NMR, your research advisor will probably explain it to you. But carbon 13 and hydrogen 1 or proton NMR are going to be really, really useful, and so we're going to focus on those. Okay, so how do these odd numbered nuclei interact in magnetic fields? Well, think of it kind of like a polar molecule with its dipole moment. Right, so if you have a molecule that has kind of a positive and a negative end to it, it has a dipole moment, and we've seen that this can interact with an electrical field and direct it accordingly. Right, so for example, if you have a cathode and an anode, a polar molecule will orient itself so that the negative half of the molecule will be facing the anode, which is positively charged, and the positive half of the molecule will face the cathode, which is negatively charged. So in a similar way, the magnetic moment of these odd numbered nuclei allow them to get aligned in a magnetic field. Okay, so it's kind of like when you have the needle of a compass, right, which is itself a small magnet, and it aligns itself with the Earth's magnetic field. It's sort of like that. Okay, so when you have a strong electric field, these nuclei act as like little magnets that like little compass needles that sort of align themselves with the magnetic field of that powerful magnet. Okay, think of it kind of like this. Like if you don't have a magnetic field, you just have your nuclei spinning around any which way. But when you apply a magnetic field, these are going to line up, so they're going to be parallel. Like the axis of these nuclei spinning is going to be parallel to that magnetic field. Now, in order to be parallel, you can either have them aligned with or aligned against the magnetic field. If it's aligned with the magnetic field, we say it's in that alpha position, and if it's against, we say that it's in that beta position. Okay, but the bottom line is that they are going to be parallel to this magnetic field. Okay, and again, you need an odd number of nucleons to have this magnetic moment in the first place. All right, so if you have an even number, they aren't capable of interacting here. It'd be like kind of like having a non-polar molecule in the presence of an electrical field. The electrical field just doesn't affect it. All right, so there is a difference in energy between these alpha and beta spin states. Okay, and this energy gap can be measured. Essentially, what we're going to do is we're going to fire radio waves at these that kind of match that energy gap, and that allows these nuclei to sort of flip from one to the other. Okay, from alpha to beta. Right, and so by varying the intensity of the radio waves, by varying their energy, which we can do by varying their frequency or wavelength, we can kind of essentially measure that energy gap off those spin states. All right. So what affects this energy gap? Well, the energy gap between those alpha and beta spin states gives us a picture of how shielded that nucleus is. In other words, how much electron density is sort of getting in between that nucleus and the surrounding magnetic field. All right. So the more shielded a nucleus is with electron density, the smaller that energy gap, and vice versa, of course. Okay, so when you basically do this flipping, right? So when you've found that energy gap, when you've got radio waves of the right frequency to do that, you say that your nucleus is in resonance with that radio wave, with that radio pulse. So hence the R in NMR. Okay, so basically, we can by looking at how these nuclei behave in the presence of these radio wave pulses, we can get a feel for those electronic environments, for that shielding or that electron density around those nuclei, and that tells us something about them. Okay, now the strength of the magnet you use, of course, will also affect this energy gap, but we're going to find a way to overcome that variance between different NMR machines. We'll talk about that in a second when we look at how to read NMR spectra. But I would be remiss if I didn't tell you that the strength of the magnet does have an effect. Okay, so the stronger your magnet, the greater that energy gap. Okay, so but again, we'll find a way to compensate for that later on. So how does the NMR machine itself actually work? How do we collect this data from our sample, right? To understand this, let me skip ahead a couple of slides. Let me show you a picture of what the setup looks like, right? So here we have our giant magnet, okay? Our sample is actually injected in through the top over here, and it's gently lowered into the heart of this magnet. Okay, now the way they get this, they generate this really strong magnetic field is your magnet is comprised of a superconducting material that they cool down to a very low temperature and use a very high current to induce a magnetic field. All right, your sample is usually contained in a very thin glass tube. It kind of looks like this. So basically you have a thin glass tube, right? Oops. Okay. You have a little small plastic cap covering it, so a little plastic stopper there, and you have your sample in here, like about, let's say, midway. It's usually dissolved in some solvent. All right. So typically we use a deuterated solvent like chloroform D here. Okay, I'll explain why that is in a second. So you have your sample dissolved in your solvent here, and now when you inject this into your magnet, you need this sample to spin. That helps get rid of the sort of unevenness of just the kind of molecules randomly dispersed through your solvent, right? It helps sort of average out all of the signals that your detector is going to see. So what we do is we actually have this NMR tube sitting in a plastic collar that has little magnets on it. So it kind of looks like this. So you have this little plastic collar thing that you insert the tube into, and the neck of this collar has little magnetic dots on it, very very weak ones, and you can cause by having a small little electromagnet in here that kind of turns on and off. It allows this to sort of spin, and again, this is a very weak magnetic field. It doesn't really interfere with the signal from your actual NMR data. Okay, so don't worry about that. But basically, it causes the sample to spin inside the NMR machine. All right. If you're wondering how do we gently lower this sample into the NMR, it actually works with a column of air. So when you open up the NMR, the system sort of blows like air at a particular pressure through this tube that you're inserting your sample into, through this column, and once you rest your NMR tube, this sort of spinner on top of there, it just kind of bobs up and down on this column of air. They gently, when you click insert, it lowers the air pressure very, very gently, and your sample gradually slides into your NMR machine. Okay? Little word of advice that I'll tell you from personal experience. If you're ever taking an NMR, be very careful that the lip of this spinner is not resting on the lip of your column, because if that's the case, it'll get stuck there while the air pressure drops until it finally just falls and clunks into it, which will cause the glass in your NMR tube to break, which will then cause the technician to have to open this up and spend several days stripping it apart and cleaning it, which will generally make him very, very angry. Okay, I may have failed my first NMR test by doing that. So just word of advice from someone who's gone through it. Anyway, so once your sample is spinning inside this magnet, what exactly is going on? Well, the machine itself also fires radio waves at your sample. As I mentioned earlier, once you've got your nuclei of your sample just sort of aligned with that strong magnetic field, and you want to pulse it with radio waves to see what is that energy gap. Like, how do we measure at what point are these nuclei in resonance with those radio pulses, right? So the machine fires a whole bunch of radio waves at it. Now, you also have a detector inside there that measures the basically when your atoms are getting excited and relaxed. It can kind of detect the change in that environment, right? It sort of can detect the sort of change in the radio pulses. And so the energy that's absorbed, okay, from those radio waves is recorded in what's known as an FID curve, or a free induction decay. So if I go back to this picture, your FID curve looks kind of like this. It looks almost like a seismograph of an earthquake happening. Okay, now this data in itself is kind of hard to interpret. So what we do is we do a mathematical transformation called a Fourier transform on this data. Okay, so it takes this sort of squiggle and converts it into a graph that has peaks. Okay, that looks kind of like this. So we call this type of NMR an FT NMR, Fourier transform nuclear magnetic resonance. Okay, so typically when people say NMR, this is what they're referring to. All right. Now, one signal by itself, just one of these FIDs aren't usually enough. Usually, you get very bad resolution in data that way. You can't be very sure of your data. So typically, what the machine does is it runs multiple of these at a time and sort of averages them out. Okay, so you get a much clearer picture that way. All right. But yeah, so that's basically how you collect data on your from your NMR sample. Okay, so your FID information is just sent to a computer that just sort of does the Fourier transform on it and gives you the data accordingly. All right. I'm not sure if for those of you who are curious about this, I don't know whether this is universal, but at least for me, everywhere that I've run an NMR, they've always used a Unix system to run it. So again, I don't think you need to get super worried if you're not familiar with that operating system. It's relatively straightforward to follow, and again, whoever's training you to use an NMR will explain the ins and outs to you. But in case you're curious, they don't make PC or Mac software to do the Fourier transform that you need. Before I forget, I mentioned earlier deuterated chloroform, right? We have to use a specific solvent when we're running our NMR. Now, why is that? Okay, well, first of all, you need a solvent that dissolves your material, and there are whole, you've got lots of different solvents that you can use. It just turns out that chloroform is just one of the most popular ones because it's usually polar enough and also nonpolar enough to dissolve a whole range of solutes, right? But why do we have to use deuterated chloroform? Why is the hydrogen in our chloroform swapped out for a deuterium? All right. For those of you who don't remember what deuterium is hydrogen 2. It's an isotope of hydrogen that has an extra neutron. Okay, that gives it a mass number of 2. So remember, you need an odd number of nucleons for your signal, for your atom to show up in your data, right? If you have an even number of nucleons, those atoms don't really interact with your magnetic field. Okay, so in other words, if we had a hydrogen here, we would in ordinary chloroform, that hydrogen would give a signal that then might get mixed up with the hydrogens of our solute, of the chemical we're actually trying to study. So by using deuterium, which doesn't show up, we don't have to worry too much about these hydrogens interfering with our signal. Okay. Again, remember, this is your solvent. You have a lot of this chloroform relative to the amount of your solute. You actually don't need a very high concentration of your sample to run an NMR on it. So if you used regular chloroform, the signal from those hydrogens would drown out the actual signal you want to see. So once your NMR data, once that FID curve has a Fourier transform done on it, you get a spectrum that looks like this, right? You have a bunch of peaks pointing upwards along your, just along this axis, right? Now, what do these peaks tell us? So just like with an IR spectrum, where there are different aspects of your data to analyze and that give you information, right? So with an IR spectrum, you have to look at the wave numbers of your peaks. You can look at whether they're broad or narrow. You can look at their strength. Are they a very intense peak, a very deep peak, or shallow? In the same way, when it comes to NMR, we get information from our different peaks, lots of different types of information, right? We're going to look at the number of peaks that we have, the number of signals we get that show up in our spectrum. So for example, in this example here, we have 3 signals that we would analyze. Okay, and the fact that there are 3 signals here tells us something. We look at where these signals show up on our x-axis. So in other words, their chemical shift. All right, so where along this this axis do these signals show up? So it's kind of like wave numbers on an IR spectrum. Right, the location of these peaks tells us something. We're going to also look at the area of these peaks, what's known as the integration. So your program that gives you the NMR data will allow you to measure the area between, you can just tell the program, just like click here and ask what is the area of this, of the graph in this region. And that will also give you some useful information about the protons giving that signal. Okay, and finally, we have the splitting pattern. Now, splitting patterns are really useful because they tell you a lot about the environment that that the atom giving that signal is in, right? So based on the atoms neighboring that atom, your signal will be split up accordingly. Okay, so for example, over here we have what's called a triplet, right? This signal is split into 3 smaller peaks. Here we have a quartet, right? We have our signal split into 4 smaller peaks. That tells us something about the nearby atoms. Okay, and that's kind of what really makes NMR useful. So let's look at each of these in turn. For the number of signals, what this tells us is it tells us how symmetrical our molecule is. The more symmetry we have to our molecule, the fewer signals we will see, because the type of signal we get from symmetrically linked protons will be identical. They kind of overlap. All right, so we see fewer signals if all of the protons are similar to each other. All right, now how are protons symmetrically similar? Well, there are 2 different ways we can look at this. We have homotopic signals and antiotopic signals. So what do we mean by homotopic? 2 homotopic protons are related to each other if there is a rotational axis that allows them to be swapped out. Okay, so for example, if you can sort of imagine, like if I look at this molecule here, again I'm comparing these 2 hydrogens over here, those 2 protons. Oh, by the way, I don't know if you've noticed, I've been using the words protons and hydrogens kind of interchangeably. These are technically hydrogen atoms, but since it's the nucleus of these atoms that interact with the NMR, remember the nucleus of a hydrogen 1 atom is just a plain proton, so that's why I'll sometimes refer to these as protons. Anyway, so what relates these 2 hydrogen atoms together is if we look at this molecule here, and you can imagine an axis going along this double bond, right? If we rotate the molecule around that, okay, this molecule is completely symmetrical. So if I were to rotate this 180 degrees, I would get the same molecule again. All right. You're going to notice that when it comes to seeing symmetry, unless you've gotten thinking 3-dimensionally down as a skill, I really recommend building these molecules as models and playing around with them. Okay, I pointed out last semester that thinking 3-dimensionally is a very useful skill in organic chemistry, but it's definitely a skill that takes a while to acquire. And in the meantime, I find building models really helps you develop that skill. So I recommend that here. So go ahead and try building models of these molecules, and you can see how rotating them will allow those molecules to, that rotating it will give you the same molecule essentially. All right, so I rotate this 180 degrees this way around this axis, and I would have the same molecule again. Same thing applies over here. For this molecule here, you can imagine the axis going down this way. So if I rotate this molecule 180 degrees that way, I would get the same molecule again. Okay, same thing over here. Okay, you can kind of imagine that axis over there, and you can rotate this molecule 180 degrees, and you'll get the same molecule. All of these examples involve a 180 degree rotation, but that need not be the case. A methyl group, for example, could have a threefold rotation, or a rotation of 60 degrees. 120 degrees. So that's something to keep in mind. So if you're having trouble seeing this with just the molecule as it's drawn, one way to try kind of test this idea of of whether two hydrogens are homotopic or not is to swap one of them out with something. Okay, and and then of course swap out the other one as well. So essentially, you're building two models, right? Now, when you do that, if you find that your two models are still identical, it means that the two hydrogens you swapped out are homotopic to each other. Okay, so for example here with this alkene, if I swap out this top hydrogen for deuterium, and then I build another model and instead I swap out the bottom hydrogen with deuterium, I would find that these two models would be the same. They're identical, right? I could just flip this molecule 180 degrees and it would match with this one perfectly, right? That tells me that this molecule over here, has these two hydrogens homotopic to each other. Okay, so that's one way to test, whether you're dealing with homotopic protons. Eventually, you'll get to the point where you can kind of just look at a molecule and know, but I do recommend trying this test out as you're trying to develop that skill. Again, with models will definitely help you out there, so I highly recommend that as you're learning this skill. Okay, another type of symmetry you'll see is when you have two protons that are enantiotopic to each other. Okay, so these will also cause these two protons to give the same signal. All right, now what do I mean by enantiotopic? Well, instead of a rotational axis, we have a mirror plane. Okay, so if you're thinking that prefix enantio sounds familiar, remember the word enantiomer, right? Those are two non-superimposable mirror images. Well, in this case, we have two hydrogens that are related to each other through a mirror plane. Okay, so so if you can imagine for this molecule here, you have a mirror plane that goes through this fluorine and this chlorine, right? So it's kind of going through the molecule, kind of just kind of bisecting this molecule in half. But this fluorine and this chlorine are in the plane of that mirror, and these two hydrogens are sticking out on either side of the mirror. It's kind of hard for me to show this on a two-dimensional screen here, but if you build this model out, you might find it a little bit easier to see that. Okay, so these imagine your plane, containing the carbon, the fluorine, and the chlorine. Okay, that's your mirror plane, and these two hydrogens are reflected on either side of that flat mirror plane. Okay, likewise for this molecule here, your mirror plane would contain all of these carbons. Okay, so all of these carbon, this is a flat molecule with the exception of this sp3 hybridized carbon here. So these two hydrogens are sticking into and out of the plane. So here the mirror plane is the plane of the screen here. Okay, of your screen, or if I were drawing this on a board, these four carbons are all in that flat mirror plane. This hydrogen sticking out of it, and this hydrogen sticking out in the opposite direction, and they're reflecting each other in that mirror plane. Again, just like with homotopic protons, you can do a replacement test here to kind of prove that you're dealing with two protons that are related through symmetry. So in this case, though, the difference is if you do your replacement test. So here we're going to swap out the hydrogen on the right to get this molecule. We're going to swap out the hydrogen on the left to get this molecule. Now, instead of these two molecules being identical, as we see in the case of homotopic protons, here we have two enantiomers, right? So if these are four different atoms now, okay, these carbons are chiral centers, and notice that these two molecules are mirror images of each other, are non-superimposable mirror images, or enantiomers. Okay, so that tells you that the two hydrogens we originally had are enantiotopic. Okay, that's a relationship. I often find students sometimes get confused between, they have a homotopic, they have two protons on a molecule that are homotopic to each other, and they look at that and they say, like, well, can't they also be enantiotopic? And there's often a little bit of confusion there because if you have a rotational axis, oftentimes you could also reflect those two hydrogens by using a mirror plane as well. Okay. This replacement test will get rid of that confusion for you because since we're defining this as these two molecules have to be enantiomers of each other, that doesn't show up. If you have two hydrogens that are homotopic to each other, they won't form enantiomers. They would still form identical molecules. All right, let me give you an example here. Let's say instead of this molecule we have here, let's say we had something similar. Let's say instead of a fluorine here, instead of a chlorine here, we had another fluorine. Okay, and let's say this was also a fluorine. Okay, so you could probably look at this and say, well, okay, now these two hydrogens are homotopic, right? I could have a rotational axis going down this way, where I can rotate this 180 degrees, and these two hydrogens get rotated into each other. But I could still have a mirror plane that contains this carbon and these two fluorines, where these two hydrogens are reflected to each other. So if this were difluoromethane, are these two hydrogens homotopic or enantiotopic? You might be tempted to say both because there is a mirror plane as well as a rotational axis, but the answer is it's just homotopic because if we do this replacement test, again, remember these are fluorines now instead of chlorines, okay, you might say to yourself, okay, are these two molecules enantiomers? And the answer is they're not, because now you have two fluorines attached to those carbons. These are no longer chiral center, and so these are no longer enantiomers. These are the same molecule, which means that these two hydrogens are homotopic, not enantiotopic. Okay, so again, that's something. If you're getting confused between whether something's homotopic or enantiotopic, doing this replacement test is kind of like a foolproof way to figure out which one you're dealing with. Okay, so watch out for that. I've just noticed in years past that that's often a point of confusion for a lot of students, especially on multiple choice quizzes, where you obviously have homotopic, enantiotopic, identical, or none of the above as kind of your answer choices for a question like this, and often students will say that, well, something could be homotopic or enantiotopic. Well, my point here is that it's not. It's one or the other. Okay, and chances are, if you're asking yourself, is it homotopic or enantiotopic, if it looks like it's both, it's probably just homotopic. Okay, so basically, if you have two hydrogens that are homotopic or enantiotopic, they're symmetrically related like that, they will give the same signal. All right, there's only one signal. So the more symmetrically related hydrogens you have, the fewer signals you get. Anytime you have protons that are neither homotopic nor enantiotopic, they're not related to each other, they are not equivalent, and therefore they will give different NMR signals. Okay, so if you have a molecule and you're trying to figure out what will the NMR spectrum for this molecule look like, it sometimes helps to look at those protons, ask yourself, how many signals should I see for this molecule? Okay, and then accordingly, when you're shown your NMR spectrum, you can see if that matches up with your expectation. Okay, so have a look here, and look at these two protons here. Well, we'll ignore the proton that's on our alcohol group for now. Let's look at just these two protons here. Okay, and of course we're going to ignore the protons on our methyl groups and the protons that's over here. Would these two protons be homotopic, enantiotopic, or neither? Okay, so try doing pause this video, replace these two protons, and compare the models of them, and ask yourself, what is their relationship? Okay, so if you've come back after trying that out, hopefully you've realized that they are not identical. Okay, so they're not homotopic, they're not enantiotopic, they are diastereotopic, which means that they would give two different signals. Okay, so if you're having trouble seeing that, the thing to realize here is that this chiral carbon here, this alcohol group is locked onto one side, right? I mean, you can rotate around this bond, but the fact is that there's a hydrogen that's not shown that's sticking into the screen over here, and this carbon is chiral and it's locked with that chirality. So depending on, so you have one of these hydrogens that's going to be closer to the alcohol group in that environment versus one hydrogen that's further away from that alcohol group. Those are two different environments. So again, if you have trouble seeing this, I really recommend building two models of this molecule. Swap out this hydrogen for a deuterium or some other colored atom, and then in the second model swap out this one, and you'll see that the two molecules you've built are not mirror images of each other. Okay, while you could consider this part of the molecule to be sort of reflective, this part stays the same, right? So your alcohol group would still be sticking out on this side on both your models, and therefore it would not be a mirror image. So it's not enantiotopic, and obviously it's not homotopic either, and that's why it's diastereotopic. We kind of, if you turn this into a chiral center, we've got two chiral centers there. Okay, and while this one's flipped, this one isn't. Okay, hence the name diastereotopic. Okay, so let's see if there are a few shortcuts here that we can take to do this. So again, like doing this the long way around, I think is a good way to sort of ingrain the understanding of the difference between something being two protons being homotopic versus enantiotopic versus not either of those. But that being said, you'll start to recognize some patterns that'll save you a little bit of time rather than having to do the replacement test every time. Okay, so for example, if you have a CH2 group, okay, so if you have a carbon with two hydrogens coming off of it, those two protons will be equivalent as long as there are no chiral centers in the molecule. Okay. If there's a chiral center somewhere in the molecule, you know that they can't be equivalent. Those two protons will be diastereotopic, not enantiotopic. Okay, like the example we just saw earlier. Okay, so as soon as we add a chiral center here, now we've got, these have two places that when we do the replacement test, this will be a chiral center as well, and that's why the relationship between these two hydrogens is not one of enantiotopicity. When you have a methyl group, the three hydrogens in your methyl group will always be equivalent to each other. Okay, you can rotate freely along that bond between the carbon of your methyl group and whatever carbon it's connected to, which will cause those three carbon hydrogen bonds to freely be homotopic with each other, right? They can rotate into each other. So methyl groups will always show up as a single peak, all right, which is very useful, okay, as we'll see later on when we get into integration. And yeah, so generally speaking, if you can see a mirror plane or a rotational axis in your molecule, you can see how your molecule is symmetrical that way. And again, that this kind of comes from some practice with thinking in 3D, with doing that work with models, so then you can start manipulating these molecules in your head without models. But if you can start seeing those mirror planes and those rotational axes, you'll immediately know whether things are homotopic or enantiotopic. All right, so let's practice that. Have a look at these two molecules here. Look at all of the protons and ask yourself, how many different groups of equivalent protons are we going to see? In other words, how many signals are we going to see? Okay, and when you have any signals that come from multiple protons, ask yourself, what's the relationship between these protons? Are they homotopic or are they enantiotopic? Okay, so feel free to pause this video and we'll come back and go through those answers. Okay, so here I've labeled each of the protons, just as, giving them subscripts of A, B, C, etc. And if they have the same subscript, the same letter, that tells you the relationship between those. That tells you that there is a relationship between those protons. So let's have a look at them here. So here in this first molecule, we have these three methyl hydrogens are all labeled HA. You could rotate freely along this bond, and so there's a rotational axis running through this bond that allows each of these to be homotopic to each other. Likewise, all three of these here in hydrogens D and all of these three here for hydrogens B are homotopic to each other. Okay. All of these other three hydrogens are all they aren't equivalent. You're going to see separate signals for these. So we would see 6 signals overall for this NMR spectrum. Okay. Now, when you're looking at this molecule, these two hydrogens here, C and F, you're probably saying to yourself, like, wait a minute, is there a mirror plane going through this molecule? The reason there isn't is because of this chiral center over here, right? This hydrogen is not the same as this methyl group over here, and that's what causes these two to be diastereotopic to each other. Okay, so they are not equivalent. For this molecule over here, notice that only half the hydrogens are labeled. That's because this molecule is symmetrical along this carbonyl. So these hydrogens here would be equivalent to the ones on this half of the molecule. So there are 3 more hydrogen A's over here, there's 2 more hydrogen B's over here, and there's 2 more hydrogen C's over here that aren't labeled. Okay. By the way, this example is a really good one of how a molecule is drawn versus how it interacts with an NMR. So even though this molecule is drawn in a very asymmetrical fashion, you have to realize that you can freely rotate around these bonds to make the molecule symmetrical. Okay, so I guess if the molecule can be symmetrical, it is symmetrical from the NMR standpoint. Okay, so that's something to keep in mind. All right, and again, these 3 hydrogens here are homotopic to each other. These 2 are enantiotopic, right? You have a mirror plane going through this molecule here that allows these 2 to be enantiotopic to each other, and likewise, hydrogen C's are enantiotopic to each other as well. An interesting situation to consider is the relationship between axial and equatorial hydrogens on cyclohexane. Now, if you were to compare axial with axial hydrogens, or even equatorial with equatorial, you could probably see that there is some homotopic relationship between them. For example, if we look at these 3 hydrogens here, and you consider a rotational axis going right through the middle of the molecule, these could be rotated onto each other by rotating the molecule 120 degrees. But what about the relationship between axial and equatorial? There isn't really a mirror plane there, or a rotational axis, but obviously there is a relationship when we do ring flips, right? So are those hydrogens equivalent or not? And the answer is it depends. When you do a ring flip, you do convert axial protons into equatorial and vice versa. And this ring flip, this conversion, happens relatively quickly at room temperature. As a result, these protons would give rise to one signal. So essentially, they are equivalent at this point. However, if you were to cool down your mixture enough, these two signals would be separate. They'd be kind of locked into, each of these protons would be locked into being either axial equatorial and stay there for the most part, long enough to give rise to two separate signals. So this actually yields something that's really interesting about NMR, in that you could take NMR at different temperatures and see how the signals change. So basically, at very cold temperatures, you would see two separate peaks, right? So they would look like that. Two separate peaks, for one for the axial and one for the equatorial position. And then as you warm it up, these peaks will start going closer and closer together. Eventually, they'll start to blur together. You'll actually start to see a very broad peak where the two peaks start to bleed into each other. And eventually, once you get to a high enough temperature, they'll both show up as a single peak. All right? It'll be a bigger peak because it'll take into account the area for both of them. We'll talk about integration in a second, but by seeing the temperature at which they go from going from a single peak into two split peaks, and measuring the distance between these and doing a few calculations, you can actually calculate the energy barrier for that ring flip interconversion. The next part of our NMR spectrum is the chemical shift. Where do our peaks show up on the x-axis? Now, for this to make sense, we need a standard to kind of give these signals context. And the standard that we use is tetramethylsilane, or TMS. TMS has 12 equivalent protons, so it's a very symmetrical molecule. All 12 of these protons give rise to a single strong signal. So you actually don't need a very large concentration of TMS. A tiny amount is added to every solvent, so that there's always some present in your sample. All right, and the machine picks up this really strong signal very, very easily. When you're analyzing your data, when you're given your NMR spectrum, one of the first things you do is you look for this strong signal and you set that as 0 on your spectrum. All other peaks, all other signals that you get from your sample are shown in relationship to this peak. Okay, so now we could just give these values this shift from the TMS peak in hertz, but there's a problem here. It's a problem I actually alluded to earlier when we talked about the different magnets that we could use for different machines, and that is with depending on the magnetic field strength you're dealing with, the strength of your magnet, these shifts are going to be different. These signals, this distance from your TMS peak will be a different number of hertz. So in order to standardize this, instead of giving the answer directly in hertz, we instead give it as a ratio to the operating frequency of the machine. So based on the strength of your magnet, this operating frequency also changes. And by dividing by it, we get a standardized answer, a standardized value that we call the chemical shift. And it's represented with the lowercase Greek letter sigma. Okay, so for example, with a 300 megahertz machine, if we look for a particular peak, that machine might give us a signal of 2,181 hertz. Now, with a weaker machine, with a weaker magnet, let's say a 60 megahertz instrument, that peak might be only 437 hertz away from our TMS peak. Okay, so if we went just by the value in hertz, this would be there'd be a huge disparity here, even though these peaks both come from the same atom on the same molecule, right? They're just in different environments, is all, or different. They're just being measured by two different devices. So to standardize this, we divide them by their operating frequency, and you can see that with the stronger magnet, when we divide by that higher frequency, we get 7.27 times 10 to the negative 6. And likewise, for the weaker magnet, we still get 7.27 times 10 to the negative 6. All right. Now, rather than giving an answer in scientific notation or dealing with a really, really small number, we instead just use the exponent there, the coefficient there, and we get rid of the exponential term. Okay, so in other words, we kind of give our answer in parts per million. So you might notice on the x-axis, the units listed there are ppm. Okay, so we would just say that the signal is present at 7.27 ppm. Right? So for proton NMRs, typically most of the signals you're going to see are somewhere between 0 and 10 ppm. They're somewhere in that ballpark. You'll occasionally get signals a little bit outside of that, but that's a little bit rarer. Okay. And of course, that's for proton NMRs. Obviously, with other nuclei, we deal with other chemical shifts. In the case of carbon-13, we'll see later on that we start getting to things like somewhere between 0 and 200. But we'll cross that bridge later. Okay, so why do your peaks, your signals, show up at different chemical shifts? We talked about that a little bit earlier when we talked about how NMR worked, and it comes back to shielding. Right, so the more shielded your protons are, the more electron density that's sort of blocking them from the influence of the magnetic field, the further upfield they are. In other words, closer to that TMS peak. All right. A quick note here, and you've probably already noticed this, if you've caught on to it. Our axis actually increases going from right to left. Okay, so the TMS peak, that 0 point, is all the way at the right, and the numbers increase as you go to the left. Okay, so upfield is to the right, closer to 0, and downfield is to the left, where you have the higher numbers. Okay, and so the more deshielded your nucleus is, whatever environment it's in, the more deshielded that nucleus becomes, the further downfield it shows up. Okay, the more it's influenced by that magnetic field. All right. So you could sort of think of it, another way to think of it in terms of that energy gap, because your deshielded protons are being influenced by that magnetic field more. The energy gap between those alpha and beta spin states is larger, and therefore, that corresponds, to an appropriate radio pulse, a higher energy radio pulse. Okay, and that's again why it shows up, downfield. So let's look at where we can see some of those typical proton signals, starting with protons attached to sp3 hybridized carbons. Okay, those are pretty common. These alkane protons generally show up somewhere in that 1 to 2 ppm ballpark, though, as we'll see, we can shift those way further downfield if we start introducing electronegative elements nearby. You can see here in this example with methane, we start off with about 1 ppm, but we start shifting further and further downfield, including all the way to 4.3 if we use a very electronegative fluorine that's 2 bonds away. All right. In addition to the electronegativity of nearby atoms, you should also consider the number of those atoms as well as the distance, the number of bonds in between your protons and that atom. So for example, here with monochloromethane, we've got 3.1 ppm for any of these proton signals that are all equivalent. And you can see that as we introduce more and more chlorines, those proton signals get shifted further downfield, including all the way as far as 7.3 ppm. in this example here, you can see that the signals for various protons show up further and further upfield as you get further away from the electronegative chlorine that causes the deshielding. So you can see that here we have these two protons that are, 2 bonds away from that chlorine, right, attached to that alpha carbon, and they show in that 3 ballpark, okay, the 3.3. In case you're wondering why it's not 3.1, the rest of the molecule has an effect here, so this is not quite the same as your monochloromethane. But anyway, it's going to still show up in that ballpark of 3.1. But you can see as we go a bond further away, now it drops down to 1.6. Go another bond further away, and you have 0.9. Okay, so the further you get away from an electronegative atom, the less your proton feels that deshielding effect. Okay, I pointed out that the type, what else is bonded to that carbon affects your hydrogens, not just the electronegative elements. So your starting chemical shift for a given hydrogen could depend on whether it's attached as part of a methyl group, as attached to part of a methylene group. That's a carbon where 2 of the other bonds are not hydrogens, and then a methyne carbon where you've got just 1 hydrogen on that carbon and it's essentially a tertiary carbon. It's got 3 other groups coming off of it, okay, that are not hydrogens. You can see that accordingly your signals should show up somewhere in each of these ballparks, and we're going to do certain calculations that help us predict what chemical shift to expect for those protons, okay, based on what other groups are attached to those carbons, okay. But these are the starting points for those types of carbons. All right, let's see some examples here. Okay, so for example, now in the case of your carbon being attached to an oxygen, that electronegative oxygen is going to shift any protons on the alpha carbon attached to that oxygen. So if your oxygen is part of an alcohol group or an ether, okay, so in other words that you've got that oxygen with a hydrogen connected to it directly connected to that alpha carbon, okay, your protons get shifted about 2.5 ppm further downfield, okay, due to that electronegativity from that oxygen. So for example, here we have a methyne carbon, a carbon with 2 hydrogens attached to it, and so your starting point for those hydrogens would be about 1.2 ppm. All right, so if I go back a slide, we got that from here, okay? There's our methylene, not methine, a methylene carbon, and there's that 1.2 ppm. Okay, so our methylene group shows up at that 1.2 ppm. We add 2.5 ppm, and so we can expect the chemical shift for those protons to show up at about 3.7 ppm. And looking at the actual NMR spectrum for this molecule, that is actually where you see it. It's at 3.7 ppm. Now, let's look at another example of an oxygen attached to that carbon. In this case, we have an ester. So that oxygen, instead of being connected to a hydrogen or an R group, as it would be for an ether, here it's connected to a carbonyl. So not only do we have this oxygen that's offering some electronegativity, but this this carbonyl over here is going to pull on that electron density. It's going to offer some more deshielding, both due to the electronegativity of this oxygen here, and also due to the resonance effects of these electrons from this double bond swinging up, okay, which would pull this lone pair from over here as well. So over there we see a shift of 3 ppm downfield. Okay, so let's see another example here. So if our methylene group starts at 1.2 and we shift 3 ppm down, we would expect our signal for those methylene hydrogens at about 4.2 ppm. Now, for this particular molecule, it turns out they actually show up at 4.1. So this is definitely not perfect, but you can see how you can figure out the rough ballpark estimate for where these chemical shifts ought to be. All right. So while you can't predict it perfectly, it at least gives you an idea of where to look for those signals. Okay. Now, if you have a carbonyl group nearby, okay, and you have the carbon of that carbonyl group, this shifts your proton's chemical shift signal about 1 ppm. Okay, so here we have a methylene group, and again, we'd assume it's shifting about 1 ppm, so we'd expect it around 2.2. For this particular molecule, it turns out that that signal shows up at 2.4. Again, not perfect, but that's a good enough estimate to know where to look for that signal. All right. And of course, there are other functional groups. These are just some of the common ones you'll come across, but there are definitely more out there. So typically, when you are trying to read an NMR, at least like if you're doing this in research and you weren't doing it on a test or something, you could probably just have a table like the one in your textbook that lists out where you would expect particular functional groups to show up. All right, so let's put this into practice. So based on the information in the past couple of slides, see if you can predict roughly where all the protons in this molecule should show up. So go ahead and pause this video for a second and identify all the protons and see if you can figure out where they'd all show up. Okay, so if you're back now, here are the answers to that to that problem. All right. So first of all, you probably want to identify the different types of protons you're dealing with, right? All of the protons on this methyl group here are going to be equivalent, as we've said before. We've got a proton that's attached to this carbon here. We've got two protons here that are not going to be equivalent. Due to this chiral center here, hydrogen B is going to be closer to that alcohol group, and hydrogen D is going to be further away. All right, so those are the hydrogens we're going to look for. Now, there is a hydrogen on this alcohol group. That's probably going to show up way downfield. There's also a possibility it might not show up very well due to just the hydrogen bonding involved. We'll talk a little bit more about that later on in this presentation. Okay, but for now, let's look at the expected chemical shifts for each of these groups. So for hydrogen A, we've got this methyl group, which we know will show up somewhere around 0.9 ppm. Now, we've got an alcohol group that's about 1, 2, 3 bonds away. So there's going to be a little bit of deshielding there. Not as much as you would expect if the alcohol group were attached, directly to this carbon. But again, you probably expect it to shift it somewhere a little bit further down from 0.9. Okay, so somewhere between 1 to 2. So hydrogen B and hydrogen D are both diastereotopic, as we mentioned. They're going to be shifted further downfield, both from this carbonyl and from these chlorines. Again, the chlorines are not directly attached to that carbon, but they are 1, 2, 3 bonds away from your hydrogen, so there's going to be some effect there. Okay, so even though these methylene carbons you'd expect them to start at about 1.2, they're deshielded another 1 ppm by your carbonyl, so you'd probably see them at about 2.2 if there weren't anything else. Those chlorines are going to shift them even further. Okay, so they're probably going to show up somewhere between 2.5 to 4, somewhere in that ballpark. Okay, again, this is not a you're just estimating where these might show up. It's not going to be perfect. And then finally, at HC, we've got a methine carbon, right? Methine proton, right? There's only one hydrogen coming off this carbon, right? So that would normally show up at somewhere about 1.7, but you've got both a carbonyl and an alcohol group attached to that carbon. Both of those are going to do a lot of shifting. 1 from the carbonyl, 2.5 from the alcohol group. So you're shifting that 3.5 ppm, so it's probably going to show up somewhere around 5 ppm. Okay, and that's basically how you'd go through that. When dealing with aromatic compounds, like benzene, for example, an interesting phenomenon you might come across is what's called diamagnetic anisotropy. All right, so even though you've got hydrogens just attached to carbons, so you expect them somewhere in that 1 to 2 ballpark. Maybe a little bit further because these would be sp2 hybridized carbons. What actually happens is your pi system, your delocalized pi system that's part of this aromatic ring, okay, which we'll go into more detail and how this aromaticity works in a later chapter. But for now, understand you've got this delocalized pi system. This system itself interacts with your magnetic field and kind of induces its own magnetic field that really shifts your signals for those protons way more than you would expect. All right, they get shifted way downfield due to the effect of this delocalized pi system. Okay, so as a result, you have that's of course for these hydrogens that are kind of pointing outwards, which is the case of for benzene. I'll show you some examples of where it actually has the reverse; it's shifted upfield. But my point here is that there's a significant shielding effect or deshielding effect from this pi system due to this induced magnetic field from this pi system. Okay, so we can see that here in the case of this benzene, these protons that are attached directly to your benzene ring. And this is a very useful thing because it really helps you identify, one, the presence of a benzene ring, and also it helps distinguish aromatic protons versus aliphatic protons. That's non-aromatic protons. Okay, so here's an example of ethyl benzene, and you can immediately tell which of your protons are on the benzene rings and which ones are on the ethyl group, right? So your benzene protons are shifted all the way between 7 and 8 ppm. They're all the way down here, okay? Whereas your ethyl group protons are here and here, okay? By the way, notice that your CH2, that's these protons over here, okay, are the ones that are shifted further downfield because they're closer to that benzene ring. They're influenced a little bit by that anisotropy, not as much as the actual aromatic protons, but again, enough to shift them further downfield. Okay, this group over here, by the way, is this methyl group at the end here. Again, that shows up in the normal 1 to 2 ppm. Okay, this is, by the way, an example of that weird scenario where you have protons that are pointing towards the center of your aromatic system. So here we have 14 annuline, and these protons here are locked kind of pointing inwards. So while these protons on the outside are shifted downfield as you might expect, they'd show up between 7 to 8 ppm, these protons here in the middle actually show up somewhere around -1 ppm. Which is, just weird. But I think I mentioned earlier that you typically have, signals showing up somewhere between like 1 and 12 ppm or 1 and 10 ppm, but occasionally you have things outside of that range. Very rarely. Well, this is one of those rare circumstances. Okay. Earlier I mentioned you find tables of of functional groups and get a feel for roughly where various types of protons will show up. And so reference tables like these are great when you're trying to read NMR, just in general, and you're trying to interpret them. For a quiz or exam, though, I do recommend getting a feel for some of the more common chemical shifts. Definitely using the example I gave you for, the difference between methyl, methylene, and methine proton and thinking about how they get shifted further downfield. Those are things you want to consider for actually memorizing these chemical shifts. Okay, but otherwise, I think in real life, you could probably just reference a table like this. Though, again, I recommend kind of getting, just through practice, you're going to get a feel for a lot of these, right? You're going to, I mentioned earlier that you have a hydrogen that's attached to a benzene ring. It's going to show up somewhere in that 7 to 8 ballpark, things like aldehydes and carboxylic acids will show up like way downfield. You'd be able to recognize those pretty immediately because, what else shows up somewhere around 10 to 12 ppm, So again, I think the general rule of thumb, of course, is also thinking about things that are electronegative nearby. That deshielding is going to shift things further downfield. And that itself also gives you an idea of what's connected to the atoms near the protons you're looking at. Okay, so the next thing we're going to look at is integration. That's the area underneath your peaks. All right, your program that you use for reading your NMR spectrum allows you to you can measure this area pretty easily, right? You just tell the program, you just like click here, and the program would tell you, okay, this is the area for that for that set of peaks. All right, and it usually gives it to you as these sort of little step curves. All right. Now, by comparing the height of these step curves, you can essentially compare the areas to each other. Okay, so for example, you can see that this peak, or this set of peaks and this set of peaks are about the same area. So they probably represent roughly the same number of protons. Okay. Likewise, this peak and this set of peaks is about the same height as well, the same area, and therefore you've got probably the same number of protons there as well. All right, that's ultimately what integration tells you. It just tells you the number of protons giving you that signal. Now, when you first tell the program to measure these, it gives you just well, not arbitrary, but it gives you just the raw numbers, right? And those numbers, when listed, seem kind of meaningless, right? So here are the actual integration values that this program gives you, and it tells you, okay, that's 27.0, that's 40.2, that's 28.4, that's 42.2. What does that mean, right? Like, do I have 27 protons on my molecule? Like, no, you don't. Of course, that's ridiculous, right? So what it tells you then is that you can then simplify that ratio, and then the numbers will start to make a little bit more sense. So to do that, typically, what most people do is they pick a region that they know has a set number of protons. So for example, if you look at this peak here, you say, oh, I know that's going to be a methyl group. I know there's a methyl group in my molecule, and that's what I expect it to be. So this, this peak over here actually represents 3 protons. So why don't I set 40.2 as 3 and scale all of these other things accordingly? All right, that's basically, and you tell the program to do that, and it automatically scales things down. Okay, in this example here, I think basically if you know that this is 1 proton, you could have it do it that way as well. So we set 27 as 1, and the program automatically calculates what these are relative to that. Okay, so it says, okay, if this is 1, this is 1.48, this is 1.05, this is 1.56. All right, so that's one approach to get started, though you can immediately see a problem here, right? You can't have 1.5 protons. So clearly, this must not be just 1 proton. So let's try doubling it, because if this is about 1.5 and this is about 1.5, if we double these numbers, we will get whole numbers here. So we do that. We set that at 2, and now the numbers start making a little bit more sense. This represents 2 protons. This represents 2 protons. This represents 3 protons. As I mentioned, it's probably a methyl group. And this represents another 3 protons. Okay? So accordingly, you can figure out how many protons give rise to that signal, and this also helps you in interpreting where those signals come from. Okay. Now, again, because we figure out this through simplifying ratios, you have to keep in mind that when you're comparing these integrals, they are relative quantities rather than an absolute number. Okay, so basically, I made the assumption there that I was dealing with a methyl group, but it could very well be that I have 2 methyl groups that are equivalent to each other. So really, that's like 6 protons. I can't tell that just directly from my NMR spectrum without some more information. Okay, so when you're predicting chemical shifts and integrations, keep that in mind. Keep in mind that you're really looking at relative numbers for when it comes to your integrals. So let's look at a couple of examples to illustrate what I'm talking about. So, for example, let's look at tert-butyl methyl ether, right? So if I were to draw that out, okay, so an ether has an oxygen with 2 alkyl groups coming off of it. So one of these is a methyl group, so this is just CH3 over here. Okay, now this is a tert butyl group, so I actually have 3 methyl groups coming off this carbon, right? And each of these carbons has 3 hydrogens. Each of those are homotopic with each other, but then they're also each set of these is homotopic with each other as well. So all 9 protons here are going to be equivalent, right? So you have 9 hydrogens over here that are going to give rise to one signal. Likewise, these 3 hydrogens here are going to give rise to another signal, okay? What does this look like when you are looking at your chemical shifts? Well, obviously the methyl group is going to be shifted a little bit further downfield because it's closer to the oxygen than these hydrogens, which have a carbon separating them. Okay, so that tells you one thing. But more importantly, the integrations, you're not going to see that this is 3 hydrogens and this is 9 hydrogens. What you'll see instead is that this set of peaks, or actually it would probably just be one singlet here. So you have one peak here. It's going to be 3 times the size of this singlet, this single peak that you see over here. Okay, I'm using terms like singlet. I'm going to explain that in a second. I believe the very next slide we're going to talk about multiplicity. But anyway, I'm getting a little ahead of myself. My point here is that it doesn't tell you, there's nothing intrinsic to your spectrum that tells you like, oh, there's 3 hydrogens here and there's 9 hydrogens here. No, you're just going to see that the peak over here is 3 times the size of this peak. Okay. Likewise here, if we look at the peaks for our 3-pentanone over here, okay, if we look at the hydrogens that are attached to these carbons, so we have 2 hydrogens here. I'll just call them HA. Okay, these are both going to be enantiotopic, right? There's a mirror plane running through this molecule, and they're in turn going to be, these 2 are also HAs, right? These two are going to be, homotopic with these 2 protons over here as well. And then we've got a methyl group here, which we'll call HB. These are all the same. And these are homotopic with these 3 over here. So HB has 6 protons, whereas HA is going to have 1, 2, 3, 4 protons. Okay, and again, your spectrum is not going to tell you intrinsically like, oh, there's 4 hydrogens in this signal and 6 hydrogens in this signal. No, you'll just notice that there's a 2 to 3 ratio, or I guess a 1.5 to 1 ratio between your 2 signals. Okay, that's all you're going to see. Now, we're going to get into splitting in a little bit. I just said signals here. HA you're going to find is not going to be a nice little singlet like your methyl group's going to be. It's actually going to be split up a little bit. Actually, I guess your methyl group here, 1, 2, 3. Oh yeah, that's going to get split as well. All right, I'm getting a little ahead of myself. Let's talk about that. So this is actually a good lead-in to our next slide. Let's talk about multiplicity. So that's the other thing we look at. What sort of splitting patterns do we observe in our signals, and what does that tell us about the nearby protons? Okay, so if you see a splitting pattern in your peak, that lets you know that there is another proton or set of protons that are just a few bonds away. Okay, so probably no more than 3 bonds away from the proton you're looking at. Okay, the more equivalent protons you have nearby, the more splitting you see. And we give names to these splitting patterns to illustrate the number of times they're split. So a singlet is just a single peak like this. A doublet involves a double peak, a triplet is a triple peak, and so on. So you have a quartet, a quintet, sextet, a septet, and so on. Sometimes, so we use these nice terms when it's really clear what the splitting pattern is. Sometimes it's hard to read what they are, especially if you have an overlap between peaks. Sometimes you have a mess of peaks, and we refer to that as a multiplet. Okay, so a multiplet is the generic term for a peak with splitting. Okay, so so if you can't tell exactly what the splitting pattern is, it's okay to refer to it as a multiplet. This happens a lot with aromatic protons. Aromatic protons all show up in that narrow 7 to 8 range, and they all like kind of overlap with each other, and there's really complex splitting patterns, and it's just a mess. So usually people will just refer to their aromatic protons as a multiplet. Anyway, let's look at where the splitting comes from. Okay, so let's look at an example here. So here we have hydrogen A and hydrogen B, and they are within 3 bonds of each other. All right, so multiplicity arises from one proton de-shielding or shielding another one. Okay, there's a slight de-shielding or shielding effect depending on the alignment of the nuclei of the protons in question. All right, so basically what happens in this example here with hydrogen A and hydrogen B is we would see a doublet. All right, now why do we see a doublet? First of all, a doublet comes when we have only one other proton doing the splitting. Okay, so hydrogen A, if this is a signal for hydrogen A, it's split into a doublet by hydrogen B. Okay, likewise, assuming there are no other protons in this molecule, hydrogen B would have a doublet for its signal as well. It would be split into a doublet by hydrogen A. Okay, there's a little bit of reciprocity here. So, where does that come from? Okay, in the case of hydrogen A and hydrogen B, one of the peaks comes from a shielding effect, or that's the one that's further upfield. The other one comes from a slight de-shielding effect. That's the one that's further downfield. Okay, let me show you how a triplet arises, and this helps illustrate where why we see different signal, why we see some shielding and why we see some de-shielding for these. Okay, so let's say in the case of hydrogen, we're looking at the signal for hydrogen A, and now there are 2 hydrogen Bs. Okay, both of these are equivalent, right? So what is their relationship to the magnetic field, and how does that affect hydrogen A? Well, if you have both hydrogen Bs against the field, they're both opposing the field, and so they both wind up de-shielding your hydrogen A little bit. That's why we see a signal going further downfield. Likewise, if both of those protons are aligned with the field, you see a shielding effect. Okay, but now there's another scenario, right? There's a scenario where you have one with and one against. Okay, that's going to be in between that. But there are 2 possible ways this scenario could arise, right? You could have this hydrogen be with and this one be against, or you could have this one against and this one with. Okay, so these are the 2 scenarios. So the probability is double for that middle scenario where one is with and one is against. Okay, and that's why since this probability is doubled, this middle signal is stronger. Okay, we see this middle peak of our triplet is double in height compared to these outer peaks of our triplet. Okay, so it's kind of a 1 to 2 to 1 ratio if you look at the height of the peaks within that triplet. All right, if I go back to this doublet, and you're wondering, okay, well, what's the relationship between these 2? They're going to be even, right? Because there's really only 2 scenarios, right? If we're looking at the effect of hydrogen B on hydrogen A, hydrogen B can either be with or against the field. So one of these comes where it's against the field and causes de-shielding, and where it's with the field and it causes shielding. And you have a 50-50 chance of either scenario being the case, and that's why we see both of these peaks having the same height. Okay? So yeah, so this is what a triplet looks like, where because we have that 1 to 2 to 1 ratio, just from probability standpoint. So you're just there are 2 opportunities to have this scenario compared to only 1 for this one and 1 for this one. Okay? So what about if we have a quartet? Okay, so let's say, this picture is a little incomplete, but let's say there was a third hydrogen B here. I should have used blue ink for this, but so you've got 3 of these hydrogens that are influencing the magnetic field with your hydrogen A. So again, you could have all 3 of them against, you could have all 3 of them with, you could have 2 against and 1 with, okay, and there's 3 scenarios where that could happen. Or you could have 2 with and 1 against, and again, there's 3 scenarios where that could happen. So now it's a 1 to 3 to 1 to 3 ratio. And that's what a quartet looks like. Okay, that's the splitting pattern we observe for quartet. Okay. Likewise, you can mathematically go through and see the splitting patterns for any of these multiplets. Okay, so for a quintet, it would be a 1 to 4 to 6 to 4 to 1 ratio. For a sextet, it would be 1 to 5 to 10 to 10 to 5 to 1, and so on. Like, you're probably not going to see too many of these. Most of the splitting patterns you're probably going to come across are going to be like doublets and triplets, okay? But, again, if you want to identify a true splitting pattern, this is how they look. I point this out because sometimes it's a little tough to tell, am I dealing with a doublet or am I dealing with 2 singlets that are close to each other, that have similar chemical shifts, that can be a little bit tricky. But the nice thing is with a triplet, because of that 1 to 2 to 1 ratio, you know that you're dealing with a triplet as opposed to 3 singlets, right? Because if you see that 1 to 2 to 1 pattern, you know that, oh, that's a triplet. All right. So what does where do we see the different types of multiplets? Now, again, it depends on how many equivalent protons are causing the splitting. So we saw that in that scenario where we had a hydrogen A and a hydrogen B, we got a doublet, right? So we had 1 neighboring proton. So if we were looking at the signal for hydrogen A, it has 1 neighboring proton, hydrogen B, and that's what split it into a doublet. Okay, so we call this the n+1 rule. You get the splitting will be 1 more than the number of protons causing it. So if we had 2 hydrogen Bs, we got a triplet, okay, because 2 plus 1 is 3. Okay, likewise, if we had 3 hydrogen Bs, we had that methyl group, that caused a quartet, and so on. All right, so a few things to keep in mind when looking at splitting. All right, splitting has to come from other protons. So if you have equivalent protons, they're not going to split each other. They're going to give rise to one signal, but you're not going to have the signal splitting itself. Okay, so for example, in this very symmetrical molecule here, we've got 4 protons. This is going to show up as 1 singlet. Okay, these 2 protons are not going to split these 2 protons because they're going to give rise to the same signal. Okay, so the other thing to consider is distance in terms of number of bonds. Your splitting protons have to be within a 2 or 3 bond distance. Once you get more than 3 bonds away, any splitting effects are so small that they aren't really observable. You don't see any splitting at that point. So yeah, so for this example here, we've got 1, 2, 3, 4 bonds between hydrogen A and hydrogen B, so you're not going to see any splitting. Okay, if there is splitting, you need a very sensitive instrument in order to notice any splitting, and even then it's kind of hard to interpret. All right, now the n+1 rule, again, it applies to protons that are equivalent. Okay, it is possible to have different types of protons splitting your signal. Then instead of seeing just a regular splitting pattern, like a doublet or a triplet or whatever, you wind up getting overlapping splitting patterns. You start getting things like doublets of triplets, or doublets of doublets, and so on. You have splitting patterns within splitting patterns. We're going to talk about that in a little bit. Okay, but here's an example of that. So if we were looking at this proton over here, okay, there are multiple protons splitting it. So there's a proton over here that's within 3 bonds. Okay, that would split that into a doublet. But there's also a proton over here that would split it into a doublet. So you would actually wind up seeing a doublet of doublets. You would not see a triplet, because this proton that's helping split and this proton that's helping split are not equivalent to each other. Okay, so we'll talk about that in a second. Okay, so let's practice this. Go ahead and pause this video and have a look at this molecule and see if you can predict the splitting. So first of all, identify all the protons on this molecule and ask yourself, what are each of these protons going to split the others into? All right, so here we have the answers. Again, all your hydrogens are labeled, and if they have the same subscript, that means they are equivalent hydrogens. If you're having trouble seeing some of those equivalencies, it might help to think about all of the carbons here except for the 2 methyl groups being in the plane of the screen, and then one of these methyl groups sticking out towards you and one sticking away from you. That might be a good way to visualize this, to see why all 6 hydrogens of these 2 methyl groups are equivalent, right? They're enantiotopic to each other. Likewise, these 2 hydrogens here are also enantiotopic to each other. Just imagine this whole, most of this molecule all being in the same plane. All right. That being said, now that you've identified which of your hydrogens are equivalent, okay, that's a very important first step. Once you do that, then you can start looking at which hydrogens are within 3 bonds of each other. So for example, if we look at hydrogens A and B, if we just pick any one of your hydrogens A, 1, 2, 3 bonds to hydrogen B, okay, and likewise hydrogen B is within 3 bonds of any of these hydrogen A's. So hydrogen A is split into a doublet because there's only one hydrogen B. Okay, remember that n+1 rule. So there's only one hydrogen B, so it splits HA into doublets. Now, there are 6 hydrogen A's, which is why hydrogen B then is split into a septet. Okay, so again, n+1. You've got 6 HA's, so there's going to be, the multiplet you're going to see is going to have 7 peaks within it. Now, that being said, there are no other hydrogens within 3 bonds of any of those, so let's start looking at C and D and E and F. C is 1, 2, 3 bonds away from hydrogen D, so C is split into a doublet by hydrogen D. There are no other hydrogens within 3 bonds of hydrogen C, so hydrogen C is split into a doublet. Hydrogen D, of course, has 2 hydrogen C's next to it, which splits it into a triplet. Okay, and then for hydrogen E and hydrogen F, they're the only 2 that are near each other, so they each split each other into doublets. When we look at the interaction between different types of protons, the gap between the peaks within the multiplets is going to be the same because they reflect the interaction of splitting between those types of hydrogens. It's going to be the same level of splitting in both sets of multiplets. So for example, if we look at hydrogen A, which is split into a quartet by the 3 hydrogen B's here, all right, we have a quartet, we can measure this distance, and it's going to be the same distance between all those little peaks. We can call that distance JAB. Okay, it's the splitting value of the coupling constant, J, and it's caused by that interaction between hydrogens A and hydrogens B. Now, if I look at the signal for hydrogen B, which is split into a triplet by the 2 hydrogens A, that coupling constant for that triplet is going to be the same distance because it involves the same interaction. Okay, this is a very useful phenomenon because it tells you which protons are are splitting each other. Okay, so in this case, if we had multiple triplets or quartets, and you wanted to figure out which ones belonged, which triplet belonged to hydrogen B or which quartet belonged to hydrogen A, you could just find the pair of a triplet and quartet that had the same coupling constant. You could measure that coupling constant using the program that gives you the spectra, your NMR spectra. Now, when we looked at NMR spectra earlier, like some examples, you probably noticed that your peaks aren't zoomed in this far. So it actually helps to do this on a higher strength instrument, just because you get better resolution. That really allows you to zoom in and measure these distances a little bit more easily. Okay. Now that being said, um, this is a very useful tool for telling which sets of protons are coupling each other, and therefore which sets are within three bonds of each other. Let's look at an example here with an ethyl group. Okay, so we know that this set of hydrogens here are going to split these hydrogens here and vice versa, right? Well, that means that then their coupling constants, those values, those J values, have to be the same. Okay? If there was another triplet here, okay, or another quartet, actually, this is probably a good example here. If these values are different, okay, as we can see in this example here, that tells us that this set of the protons that are causing this signal are not splitting the protons causing this signal, and vice versa. Okay, because the fact that these J values are not the same tells you that they are not splitting each other. Okay, they belong to some other hydrogens on this molecule. Okay, so that's something to keep in mind when it comes to determining which hydrogens are connected to where in the molecule. Now, one of the neat things about this ethyl group here is the fact that you have this methyl group here with three hydrogens, and this CH2 group, this methylene group here, with two hydrogens, and they cause each other to split, right? They're going to be within that three bond range. So your methyl group is going to be split into a triplet by the two hydrogens of your methylene, and likewise your methylene is going to be split into a quartet by the three hydrogens of your methyl group. Okay, this combination of a quartet and a triplet with integrals of two hydrogens and three hydrogens respectively is unique to ethyl groups. Okay, it's kind of a very identifiable signature, a fingerprint, if you will, for an ethyl group. So that's something you want to keep in mind if you're looking for an ethyl group, or if you notice this pattern, it's kind of indicative that your molecule has an ethyl group in it. Likewise, there are other patterns out there that are quickly identifiable. If you have a singlet that has 9 hydrogens in it, that's a very unique scenario. That's indicative of a tert-butyl group. Because all 9 of these hydrogens are equivalent to each other, and because of the nature of a tert-butyl group, there isn't going to be any hydrogen within 3 bonds of this system to split those hydrogens, so they're going to show up as a singlet. Okay, so having 9 protons in a singlet is kind of unusual, and that should immediately tell you like you're dealing with the tert-butyl group. A septet, next to a doublet should immediately tell you you've got an isopropyl group. Okay, again, an isolated one. If you've got hydrogens coming off here, that might affect the splitting on this hydrogen, where we're going to get into that. It's getting into the whole like doublet of doublets and things like that I mentioned earlier. So I'm getting ahead of myself a little bit. Let's focus on our isopropyl group here. But the 6 hydrogens of your 2 methyl groups here are going to be equivalent to each other, okay, and they get split into a doublet by this one hydrogen that's different. Likewise, this one hydrogen is split into a septet by the 6 hydrogens of the 2 methyl groups coming off this carbon. Okay, so it's basically a very similar setup. We kind of saw this in that example a few slides ago. All right, so I've alluded so far to things like doublets and doublets of triplets and other overlapping splitting patterns. These come about when you've got hydrogens that are within range of multiple types of other hydrogens, other protons. So hydrogen B in this example is illustrative of what I'm talking about. So if we look at hydrogen B, it can couple with the three hydrogen A's. These three hydrogen A's would split hydrogen B into a quartet. Likewise, the two hydrogen C's here would split hydrogen B's into a triplet. So what do we see? Well, the thing is, the coupling constants for both of these interactions is not the same. The coupling constant for AB is not going to be the same as the coupling constant for BC. Now, it depends which one's greater. Let's say AB is a greater coupling constant than BC. Then what we would see is a quartet of triplets that look like this. Okay, so basically, if you want to measure the coupling constant for BC would be the coupling constant you measure in each of these little triplets, and they would be the same value. Okay, because remember, it's the two hydrogen C's that are splitting hydrogen B's into that triplet. And if you want to measure the coupling constant for AB, you would measure from, let's say, the middle of one triplet to the middle of another. Okay, that distance is the coupling constant for AB. Okay, and again, we see a quartet here because there are three hydrogen A's splitting your hydrogen B into a quartet. Okay, now it's possible to have the opposite scenario. Let's say the coupling constant for BC is greater than that of AB. Well, instead, you will see a triplet of quartets. Okay, and so this is what that would look like. It's you've got your triplet system, but each triplet itself is split into a quartet. Okay, now this is when there's a clear difference between those coupling constants. Occasionally you get scenarios where those coupling constants are very similar. And then the overlap gets really messy and it's hard to tell what's going on. This is a scenario where you would just describe this as a multiplet. You just have a whole bunch of peaks together and it's really hard to discern what exactly is in there. Okay, so it's okay to describe that as just a multiplet. I think we've seen examples of this out in that aromatic region for certain aromatic compounds. All right, so let's go ahead and try a practice problem on this. So go ahead and look at the hydrogen on this molecule here and see if you can figure out what its splitting pattern would be like. Alright, so if you pause this and join us back again, hopefully you've realized that this hydrogen over here is split into a doublet by the hydrogen that's over here, but then we've got another hydrogen that's over here in a different environment that then splits it into a doublet as well. Now, these are different types of hydrogen, so those coupling constants are properly different, so you'll see a doublet of doublets. Okay, so basically, if you want to see what that looks like, it would look something like, basically, you would see kind of a pair of doublets with a small coupling constant, and another pair of doublets with the same coupling constant, but the coupling constant between those two pairs is not the same. Okay, so something like that. Okay, would probably be your peaks. Yeah, so that's basically how you'd go about that. By the way, if you're writing this out, the abbreviation you would have for this would you just write a double D for doublet of doublets. Okay, so typically you use the letters, S for singlet, D for doublet, T for triplet, Q for quartet, things like that. But basically, once you start getting into these sort of more complex splitting patterns, you just pair these letters together. So actually, if I go back a couple of slides, so here we have a quartet of triplets. So we would write that out as QT, quartet of triplets. Whereas on the next slide, we have a triplet of quartets. So that would be TQ. Okay, so something to keep in mind for how we'd label that if we were writing these out. Okay. So so here's an example of a situation where we don't see coupling. So I think earlier I alluded to the fact that alcohol protons are a little bit weird, and so you can see in the scenario here that the hydrogen on our alcohol group does not split. Even though the the CH2 of our ethyl group is split into a quartet by the the CH3 over here, um, it's not being split any further by the hydrogen in your alcohol. Okay, likewise, your alcohol, as I mentioned, is a singlet. It's not being split by the CH2 group either. Okay, so this is an interesting scenario with hydroxyl with the alcohol protons or hydroxyl protons, um, and this comes about from their intense hydrogen bonding, but rather more like their acidity, actually, I guess. Basically, we label these types of hydrogens as labile, meaning that they can come off of the molecule uh, relatively easily in the presence of an acid, especially. Okay, so due to this exchange of protons, due to the easiness, the ease at which these protons are plucked off, they don't really behave like normal protons that are there all the time. And so we don't see these coupling effects that we normally would, those splitting effects that we would typically see. Okay, so oftentimes you'll see a broad singlet for an alcohol group like that. Okay. Now, if you want to try to avoid this phenomenon, it sometimes helps to try and get rid of any traces of acid that might be present that sort of catalyze this process. Of course, that sometimes can be a bit of a pain. So sometimes it's easier just to, you know, just go in expecting that your alcohol peak might not show up. But that being said, if you take these precautions, then it is possible to see the alcohol peak and the splitting caused by it. Okay, aldehyde protons will often appear as a singlet as well, and that's due not that they're labile or anything like that. They're attached to a carbonyl carbon, so that's not a very acidic location. But it's just that the coupling constant is so small that you don't see any splitting effects from that proton. So if you place one of these molecules that are capable of hydrogen bonding, or that especially are particularly acidic, into a deuterated solvent, as is often the case with NMR, these signals wind up disappearing. Your hydrogens wind up being exchanged for deuterium atoms, and as we've said before, deuterium doesn't show up on your NMR spectrum, right? It's an even number of nucleons there, so that's something to keep in mind with protic molecules like these. Okay, so here's where we kind of bring everything together. Let's look at a molecule like this one and identify all the protons in there. So first of all, ask yourself, are any of these protons equivalents, right? How many different signals would we expect to see? How many peaks would we see? And then predict roughly where they'll show up. Okay, so roughly what their chemical shift is going to be. What's the integral of those of each of those shifts? So how many protons do they represent? And any splitting pattern you might expect. Okay, for those sets of peaks. All right, so go ahead and write that out, and yeah, pause this video, and I'll come back with hopefully a spectrum of what that looks like. Okay, so hopefully you've joined us again now after pausing this video, and here's what this answer looks like. So when we identify all the protons on our molecule, you can see that here this methyl group has equivalent hydrogens here. Those are all homotopic to each other, so we can label that as hydrogen A. We've got these two protons here that are identical, and then same with these two here. So those give rise to individual signals, but hydrogen, oh sorry, not individual, you know what I mean, like a group of signals for each pair here. So hydrogen C for both of these, hydrogen B for both of these. Each of these hydrogens, though, of course, are individual ones with separate signals. If you're wondering why aren't hydrogen E and hydrogen F identical, they're kind of locked into place by that double bond. Hydrogen E is closer to the rest of this molecule whereas hydrogen F is closer to this methyl group, and they're locked in that position. So that's why they're not in the same environment, and that's why they have separate signals. Okay, so let's look at the signals we would see. So hydrogen A, of course, that methyl group, which would normally show up around 0.9, but due to the presence of this double bond, the electron density here kind of de-shields that a little bit and sends it a little bit further, downfield. Okay, so if you originally predicted this being somewhere around the 1 ppm mark, it's further than that. Okay, so something to watch out for. Now, there isn't anything within 3 bonds that can split hydrogen A. Okay, if the nearest neighbors are hydrogens, D, E, and F, and they're 1, 2, 3, 4 bonds away at least, and so hydrogen A just appears as a singlet with an integral of 3. Okay, hydrogen B over here is close enough to hydrogen D to be split into a doublet by it, and since there are 2 protons here, it'll have an integral of 2. Hydrogen C is a singlet. It's kind of isolated. There's nothing near enough to split it, and again, it'll have an integral of 2 because both these hydrogens are equivalent to each other. Hydrogen D is, hydrogens D, E, and F will each have integrals of 1. Hydrogen D is close enough. It's within 1, 2, 3 bonds of hydrogen B, so it gets split into a triplet by the 2 hydrogen Bs. Hydrogens E and F will split each other, but they aren't close enough to anything else to be split any further. So you actually don't see any complex splitting pattern here. Hydrogens E and F are each doublets. Okay, so you can see this is kind of what those peaks look like. Hydrogens E and F, of course, are really close to that alkene, which is why they are split so far down. They're de-shielded and therefore sent so far downfield. Okay. Hydrogen F here is being labeled as the one that's kind of further downfield. I'm not sure necessarily if that would have been the case. Like I would have thought that hydrogen E perhaps would be a little bit further downfield due to some of the interaction with this carbonyl group here. So if you flipped E and F, I think that's a totally legitimate answer. Okay, so don't read too much into the locations here. If you've got the right ballpark, you're probably okay. All right. For hydrogen C and D, if you're wondering why they show up where they do, again, keep in mind that hydrogen D is next to a carbonyl carbon. Okay, so it's a methine carbon, and it's next to a carbonyl, which sends it, 1 ppm further. And keep in mind, of course, it's also near that alkene, which sends it even further than you would expect. Okay. Hydrogen C over here is in between 2 carbonyls, so it's actually sent, it's a methylene proton that's, that's sent 1 ppm downfield by each of these carbonyls, so 2 ppm in total. Again, that's why it shows up somewhere around 3.2. All right, so when it comes to just quickly reading a proton NMR, it can help you really distinguish between multiple options. Sometimes you don't even have to do a very complex analysis. Something as simple as the number of signals here will tell you the difference between these different isomers. Okay. Something like IR or mass spec won't be able to do that. They'll each tell you what pieces you have, but due to the ability of NMR to tell us, to give us different signals for protons that are in different environments, but signals for protons, one signal for protons that are in the same environment, that are either homotopic or enantiotopic, we wind up getting more information about, just like in what order are these things arranged? Okay, and that's not even getting into splitting patterns, which of course will tell you even more about how things are connected to each other. So you can see here, just looking at the symmetry of these molecules alone, you can figure out how many signals you would expect. And so even just like glancing at the NMR spectra for these three molecules, you'd be able to tell which one's which. Okay. So yeah, so over here you can see that if you're having trouble seeing where all this symmetry comes from, if you look at this molecule here, you could consider this being a rotational axis running down this way, or a mirror plane, but rotational axis is a higher level of symmetry. So, this methyl group gets rotated into this methyl group, this hydrogen gets rotated into this hydrogen, and this one into this one. So you'd see three signals because those are three sets of different hydrogens. Okay. Over here, if you still have that rotational axis over here, but now we have a proton over here that's lying in that axis along with this one. But these are not equivalent to each other, right? This hydrogen's in between these two methyl groups. This one is not. It's further away from those methyl groups. Okay, so we'd see four different signals for this one. This one over here is really interesting because you've got a higher level of symmetry. You've got that same rotational axis that runs this way, but notice that there's also a rotational axis that runs this way. Okay, so both methyl groups are reflected or rotated into each other by the axis that runs here. But if you picture, and actually this hydrogen's rotated to this hydrogen, and this hydrogen's rotated to this hydrogen. But the rotational axis that runs, from left to right here would rotate these two hydrogens into each other, and that's why all four of these hydrogens are identical. Okay, let's practice this. Here are two molecules that again are very similar, have all the same functional groups, have the same molecular formula. So IR and mass spec aren't going to help here. Take a second and think about how the NMR spectra of these two molecules might look a little bit different. If you're not sure where to begin on this problem, my advice is to start just identifying the numbers of hydrogens that are equivalent and the splitting patterns for each set of hydrogens. Don't even worry about chemical shifts. Just the splitting pattern and the number of signals alone should probably be enough to distinguish these two molecules. All right, so let's try drawing this out. So, for example, here we have this methyl group. Okay, so that's going to be three hydrogens over here, and the only thing that's near enough to split them would be this hydrogen over here. Okay, so we know that this is going to be split into a doublet by that. Likewise, this hydrogen here, which will have an integral of just one hydrogen, it's going to be split into a quartet by the three hydrogens of our methyl group. Okay, so that's going to be a quartet. There's no hydrogens here. There's three hydrogens here. The three hydrogens here, of course, though if you look at the nearby neighbors, I think the nearest hydrogens are the ones here and here. Those are too far away to split them, right? It'd be 1, 2, 3, 4 bonds away, so it's too far, so this would show up as a singlet. Okay. Now here we have two hydrogens, all right, so we'll have an integral of two hydrogens. Again, we established that these hydrogens are too far away to split that. 1, 2, 3, 4 bonds away. But over here we have two other hydrogens, and those would be only 3 bonds away. Okay, so we've got two hydrogens here. Okay, so this would be split into a triplet by these two hydrogens here. Now, these hydrogens are interesting because they're not only close to these ones, but also this hydrogen that's over here. Okay, so you've got a hydrogen here. So this would be split either into a doublet of triplets or a triplet of doublets. So I'll just say dt over here, but just understand this could also be a triplet of doublets depending on the coupling constants. Here, this is going to be split into a triplet by the two hydrogens here. We also have a hydrogen here and a hydrogen here that are within range to split this. So this is actually going to be some sort of multiplet. It could be a doublet of triplets or some combination thereof. So I'm just going to call it a multiplet here because it's going to have some complex splitting pattern. And then of course we're going to have two different hydrogens here. They're in different environments. So these are both going to be, again, split into doublets of doublets by this hydrogen here and by each other. Okay, so we have one hydrogen here that's coming off that's going to be a doublet of doublets, and one hydrogen here that's going to be a doublet of doublets as well. Okay, now let's try looking at the hydrogens on this molecule here. Okay, so here we have a our methyl group, and actually over here, just overall, this will be like an ethyl group splitting pattern. So we have a set of 3 hydrogens here that's going to be split into a triplet by these 2 hydrogens here. Okay, and these 2 hydrogens here, we've got 2 hydrogens here, they're going to be split into a quartet by these 3 hydrogens, and that's it. I don't think there's any other hydrogens nearby enough, so that'll be a quartet. Okay, and then over here we have, again, we're going to have 3 hydrogens that'll be a singlet, because I don't think there's anything else. Actually, wait, hold on. 1, 2, 3, 4. Yeah, there's nothing else that's close enough to split that. This hydrogen here will have 1 hydrogen. It's going to be split into a triplet by the 2 hydrogens that are here. These 2 hydrogens will be split accordingly into a doublet by the hydrogen that's coming off here, and a doublet by the hydrogen that's over here. So doublet of doublets. We've got a hydrogen here that's going to be split into a multiplet, right? We've got 2 hydrogens that would split into a triplet, plus the 2 hydrogens here. Essentially this whole scenario that we saw over here. So 1 hydrogen that's a multiplet, and again, 1 hydrogen that's a doublet of doublets, another hydrogen that's a doublet of doublets. Okay, so again, you can see some similarities here, but I think the immediate thing that you're going to notice that tells you that things are different is the fact that you're going to see a peak with 3 hydrogens, an integral of 3 hydrogens, that's a triplet. Okay, whereas for this molecule it's going to be a doublet. That would immediately tell you the difference there. And of course there are other differences as well, like this one over here is a doublet of triplets or a triplet of doublets, whereas here it's a doublet of doublets. But I think, again, this peak here is the one that's going to be the easiest to tell the difference there. Okay, so I probably did a little bit more work than I really had to there by labeling everything. But yeah, that would be a quick and easy way to distinguish between these 2 molecules. Alright, so when it comes to analyzing proton NMR spectra in general, okay, and if you've got the formula of the molecule that you're dealing with, you need to sort of look for the pieces that your molecule has, and then use your proton NMR to think about how those pieces are connected together. This is definitely an acquired skill. It takes a little practice. It takes a little getting used to. But eventually, the more you practice this, the more second nature this becomes. Just this sort of analytical approach to figuring out the formula of the structure of an unknown. Okay, so first of all, start off by asking yourself, how many degrees of unsaturation does it have? That's something we picked up in the last chapter, but that's really useful for determining things like rings or double bonds or triple bonds. Okay, that can go a long ways towards figuring out what helping explain the location of certain functional groups. Okay. Now, then you want to think about the number of signals you see in your NMR, and that'll tell you a little bit about the number of environments you have, or how many protons might be similar. Okay, of course the integrals there will tell you the number of protons that are similar, but yeah, basically you want to try and think about how many sets of signals do you expect to see, how many sets of protons are going to be in symmetrical environments, right? And that kind of gives you a feel for the symmetry of the molecule in general. Okay, so once you've got the pieces together, start looking at things like the multiplicity and try to get a feel for what pieces are connected to each other, all right? And think about how near they might be. Okay, so you can also, once you start getting a a picture in your head of what the molecule might look like, or you start like do trial and error in your way towards it, use this to sort of confirm if you're on the right track. If a two pieces are connected to each other, would you expect to see the multiplicity that you do? Okay, if you don't, then that might confirm that that's not a good model that you drew, and that you have to try and play around with it a little bit more. Okay, so be very careful about shoehorning things, trying to like think that you've got the molecule right and fitting the data to it. It's the other way around. You want to use your data to help rule out potentially wrong molecules. Okay, so always be on the lookout for pieces of data that actually prove your molecule wrong. Okay, that let you know if you've got to tweak it more. All right. So yeah, let's try and piece all of that together and do a practice problem involving all of those. So here we have a molecule with the formula C7H13Cl, and we are given its NMR data. Okay, so let's start off by figuring out the degrees of unsaturation. So if we've got 7 carbons, 2n plus 2 is 16, so there ought to be 16 hydrogens. But there's only 14, right? If you treat the chlorine like a hydrogen, that tells us there's 1 degree of unsaturation in there. Okay. Then also notice that we have 1, 2, 3, 4, 5 signals. Notice the integrals. They also kind of help you group together your your bunches of hydrogen. So the fact that here we have a singlet that has 6 hydrogens tells us that we probably have 2 methyl groups that are equivalent that are a singlet, so they're not close enough to any other hydrogens that would split them. Okay, so that's something to keep in mind. Yeah, and it looks like we've got another 3 hydrogens here, so that's probably another methyl group. Since that's a doublet, it's close to another isolated hydrogen. Okay, and things like that. Like here we've got a doublet of quartet, so we know that we have 1 hydrogen that's close to another single hydrogen, but it's also close to a triplet, so or not a triplet, but close to a methyl group probably. Okay, so it's probably close to this one that splits it into a doublet. So this is a kind of what I'm talking about. You've got to try and get a feel for like how things are connected together like that. And again, don't panic if you're not good at it immediately. This is one of those skills that takes a little while, takes a little bit of practicing to get the hang of. Okay. All right, so hopefully you got something that looks like this. All right, so if you're having trouble figuring this out, like I said, look at the different pieces you've got. First of all, we've got a degree of unsaturation, so we know we've either got a ring or a double bond. The fact that we've got signals that are showing up so far downfield, I don't think we could attribute that to the chlorine alone. So that probably indicates that it's more likely we have a double bond as compared to a ring in this molecule. Okay, so again, like the fact that we've got two methyl groups here that are isolated, that would be these 2 methyl groups here. There are no protons near enough to split them, which is why they show up as a singlet. We've got another methyl group over here, split into a doublet, so it has to be close enough to only 1 hydrogen to split it. That'd be this hydrogen here. Okay, this is the one that's going to show up as a doublet of quartets, right? It gets split into a quartet by these 3 hydrogens here, and it gets split into a doublet by this hydrogen here. Again, notice how far downfield it is. That tells us something about the fact that it must be on our alkene. Okay, likewise, we must have another hydrogen here that also that's split into a doublet by this hydrogen, and that's also fairly downfield, and that's this hydrogen over here. It's got an integral of 1 hydrogen, and it's a doublet. Okay, and then finally we have these 2 hydrogens here that show up as a singlet because there's nothing near enough to split it. While that would be a methylene set of hydrogens, notice that it's sent further downfield, so that tells you it must be close to either the double bond or the chlorine. in this case, the chlorine. Okay. Now, if you looked at that and you're saying like, oh, I have no idea how we got from point A to point B there. That was really difficult. Again, I want to reassure you that this isn't an easy skill and it takes a little practice. But I also want you to remember that your quizzes and exams are all multiple choice. So if you do ever get stuck, do consider trying to do this backwards. If it's more difficult to go from just a list of peaks and try to create a molecule from this, you can work backwards and look at your answer choices, which are molecules, and ask yourself what would the spectra, what would the peaks, the signals for that molecule look like, and then see which ones agree with the question. Okay, so I could like identify basically all of the parts of this molecule. Okay, and that might be quicker and easier. So I might say, okay, going through this, I have a methyl group here, so that's 3 hydrogens. Okay, it's only close to this hydrogen here, so that's going to be a doublet. I've got 1 hydrogen over here. It's going to be split into a triplet by these. It's going to split into a singlet, into a doublet by this, so that's a doublet of triplets or a triplet of doublets. Okay, I've got 1 hydrogen over here. It's going to be split into a doublet. All right, and there's nothing else near enough to split it. I've got 2 methyl groups here, so that's 6 hydrogens, and there's nothing near enough, so that's going to be a singlet as well. Okay, and then of course here we have 2 hydrogens, and again, nothing near enough to split that, so that's going to be a singlet. Basically, you could just do that really quickly for all of the answer choices, and ask yourself which one of those answers that matches up with the question. Okay, and in this case, a molecule that looks like this would be the right answer. All right, so again, don't panic if you're having trouble moving in one direction. There's always the opportunity to go in the opposite direction to work things out. Okay, so up until now we've been talking about proton NMRs. We'll end this chapter talking about carbon-13 NMRs. All right, now proton NMRs are quick and easy to take. Like you can run a proton NMR in less than 15 minutes. So I remember being in grad school, just being in my lab, like in the span of a few minutes, just booking an NMR slot that happened to be open, creating a sample, running down, taking an NMR, and running back. It's one of those things that you just do routinely, and it's relatively easy to get done. Carbon-13, on the other hand, involves a little bit more work. It takes a little bit longer to gather enough data to get a decent spectrum. The reason for this, and so instead of just running one in 15 minutes like proton NMR, you'd actually try and run those overnight, or at least have a large enough block of time, of a few hours to collect enough data to get a good high resolution spectrum. All right, now the reason for this is that carbon-13 is far less abundant than protons. Okay, so while hydrogen 1 is the most common isotope of hydrogen, carbon is mostly carbon-12. Carbon-13 only accounts for about 1% of all carbon. So you need a very sensitive setup, a very sensitive instrument, and a concentrated sample in order to get a good amount of data. Okay, in addition to just having your sample, your NMR machine work for a while to collect enough consistent data to give you a good spectrum. Okay, now there are other differences, as we'll see now when it comes to analyzing the spectra. In a proton NMR, you get a lot of information about things like chemical shift, splitting patterns, integration, all of that fun stuff. In the case of carbon-13 NMR, you only can get information from the number of signals you're expecting and their chemical shifts. You do not get any splitting patterns. You aren't able to get any integrals. So you're kind of limited in terms of the data that you can get out of your carbon-13 NMR. Okay, the kind of the meaningful information you can get out of that carbon-13 NMR. But that's okay. You can still get a lot of useful information there. Keep in mind, you've got fewer carbons than hydrogens in your molecule oftentimes. So even this limited data is very important for telling you what your molecule has. Okay, just the number of signals alone can tell you a lot and help distinguish between multiple options. Okay. Now, the reason for this, the reason we don't have coupling and things like that, there is you can get some really complex splitting patterns if you did try to look for coupling and coupling constants and stuff like that. So generally, to make the spectra a little bit easier to read, we have what are called decoupled spectra. Okay, so that's why carbon-13 NMR are decoupled. You only see singlets for all of your signals. Okay. All right. Another thing you'll notice in terms of the difference between a proton NMR and a carbon-13 NMR is just the range on your x-axis of where you see signals. Instead of seeing signals between 1 and 10 ppm, you actually wind up having a very large range from 0 to 220 ppm. Okay, when you compare to your TMS standard. All right, so yeah, so basically it's a much larger range. You've got just singlets in there. So seeing where on that range your singlets are, and just like knowing from your molecule, like how many signals would I expect, that alone should give you a lot of information. Okay, so let's see some examples here. So let's say we are comparing these three isomers of xylene, right? Again, just by sort of vetting how many signals would I expect, how much symmetry do I have in this molecule, would allow you to immediately distinguish between these. Okay, so for example, over here, we would get 4 signals. So we have this rotational axis over here. So this methyl group gets reflected into this one, this carbon over here, and so on. We have 4 different, unique environments. Okay, out of our 8 carbons. Over here, we have 5 different signals. 2 of them lie on that axis. Okay, so again, out of our 8 different carbons, we have 5 different signals. Yeah, so this methyl group is going to be the same as this one. This carbon here is going to be the same as this one, and this one is the same as this one. All right. Over here, we have multiple axes of symmetry, and that really cuts down the number of signals we see. We have only 3 signals, okay, because this carbon is similar to this carbon when you rotate this way, but then this carbon is similar to this carbon when you rotate this way. And so that's why all 4 of these carbons are going to be identical to give rise to one signal. This carbon is rotated into this one, so these 2 signals are identical. And this carbon, this methyl group, is rotated into this one. So again, that gives rise to only one signal there. Okay, let's try and put this into practice. Look at this molecule here and ask yourself, how many signals would you expect to see? Okay, so you probably notice there's only 6 carbons here, so you can't have more than 6 signals. So you want to think about how symmetry cuts down those number of signals. If you imagine a rotational axis going this way, this carbonyl carbon is rotated into this carbonyl carbon, so that would give rise to one signal. Okay. Likewise, this carbon here is rotated into this one, and this one into this one. Okay. So these wouldn't be separate unique signals. You'd see one signal for each of these sp2 carbons. But then also you could rotate, if you imagine a rotational axis over here, this carbon gets rotated over here. Okay, so all 4 of these carbons are going to be identical. So you would only see 2 signals for this carbon-13 NMR. Now, I mentioned that chemical shifts tell you a lot of information as well. So depending on the type of, the environment, the type of bonds your carbons have, they'll show up in different regions of your 0 to 220 ppm range. All right. So if you have a carbon with only single bonds, an sp3 hybridized carbon, it will typically show up between 0 and 50 ppm. Between 50 and 100 ppm, you'll see sp hybridized carbons, as well as carbons connected to electronegative elements like nitrogen or oxygen. okay, through single bonds at least. Between 100 and 150, we have carbon sp2 hybridized carbons, whether they're part of an aromatic system or aliphatic here, like this alkene. And then over here, between 150 and 220, we have sp2 carbons that are part of a carbonyl that are double bonded to an oxygen. So again, please note the difference here. Here we have sp2 carbons that are connected to other carbons, right? Only to other carbons. Here we have single bonds to nitrogen and oxygen. Okay, whereas here it's a double bond between the carbon and the oxygen. So that really sends these pretty far downfield. Okay, so with that in mind, let's practice this. So go ahead and identify the different carbons in this molecule and predict roughly where those chemical shifts are, where those signals are going to show up on your carbon-13 NMR. Okay, so hopefully you've figured out that we've got 6 carbons in this ring, plus another 3 carbons over here. Okay, so that's 9 carbons to account for in total. Okay, and so let's look for the corresponding chemical shift. So each of these carbons is going to be kind of unique. They forgot to label this carbon here. There's a 9th carbon that they forgot about. So that's actually going to show up kind of in a similar range to carbons 4, 5, and 6, where, in that sp2 carbon range of 100 to 150. All right, so carbon 1 over here, this methyl group, it's going to show up between 0 and 50. They've kind of gone, this answer key has gone a little bit into more detail than I would expect you guys to figure out from this slide. If you guess somewhere between 0 and 50, that's fine. You don't have to say between 20 and 30. Okay, so if you didn't get that, get things narrowed down that far, that's okay. All right, yeah, so that methyl group is going to show up between 0 and 50. Carbons 2 and 3 are also sp3 hybridized carbons, and so they show up in that 0 to 50 range. It's just that they're going to show up a little bit further downfield since they're so close to to carbonyls. So I would imagine carbon 2 is probably further downfield than carbon 3 because it's in between 2 carbonyls, whereas carbon 3 is only next to 1. Okay. Carbons 4, 5, and 6, and of course the unlabeled one that they forgot, are all sp2 hybridized carbons that show up in that 100 to 150 range. C7 and C8 are both carbonyl carbons, so they're going to show up in that 150 to 220 range. Okay. All right. So again, you're kind of limited a little bit when you do your carbon-13 NMR. You can still get a lot of useful information, but due to that, the decoupling there, you don't get any splitting patterns. So it kind of doesn't tell you a lot about the hydrogens and things that are connected there. That being said, it is possible to do what we call a DEPT or DEPT carbon-13 NMR, which stands for distortionless enhancement by polarization transfer. Basically, while a fully decoupled carbon-13 NMR spectrum shows all of your carbon signals, these depth NMR will cut out some of the signals. They give you limited signals, or in the case of depth 135, kind of give you a negative signal for a methylene peak. And so these peaks either disappearing or looking weird give you a feel for how many hydrogens are connected to those carbons. Okay. So this is kind of the difference between your typical decoupled spectrum, depth 90, and depth 135. Okay, so depth 90, of course, like the regular spectrum will have all carbons show up. But for depth 90, only methine carbons show up, and for depth 135, methine and methyl carbons show up as regular peaks, but methylene carbons have negative peaks. Okay, so with that in mind, have a look at these two molecules and ask yourself, how could depth carbon-13 spectra tell the difference between these two? All right, so if you're having trouble seeing it, it's probably because you've probably noticed that you've got similar numbers of methylene and methine carbons, right? We have 5 carbons that are CH2s, right? And 1 carbon that's a CH carbon, right? So on our molecule over here, this is a CH2, so methylene, 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 and then a methylene over here with our methine over here. Whereas for this molecule, these 5 carbons are CH2s, and this is our carbon with only 1 hydrogen coming off of it. So what's the difference there? Well, basically, it's which one is closer to your OH group. All right, so remember, your oxygen and your alcohol group is going to send things downfield, right? Because it's going to sort of de-shield things. And so if you're looking for that sole CH peak, that methine peak, ask yourself, well, is it the furthest downfield peak that I observe, right? Do I notice that it's really far downfield, like it is because it's right next to that alcohol group? Or is the furthest downfield peak one of these CH2s? In order to distinguish these, of course, you need to run this as a depth 135. So if I go back 2 slides, you can see that those CH2s will show up as negative peaks, right? Peaks that are pointing downwards below your x-axis, whereas that methine peak would be the only positive peak. Okay, so that would be relatively easy then to distinguish them. So if you see that sole positive peak, furthest downfield, then you know it is cyclohexanol over here. All right, so we've mostly been looking at these from an organic chemistry utility standpoint. NMR, I've probably hopefully impressed upon you, is a very, very useful technique for organic chemists. But that being said, this technology has very wide-reaching scope. You've probably heard of MRI, or magnetic resonance imaging, and it works on a very similar phenomenon. Basically, instead of looking at the environment that the atoms in your sample are in, you start looking at the atoms in tissue, in biological tissue. You're putting your sample, in this case it's the body of the patient you're examining, in the presence of a powerful magnet, and just making a note of how the atoms of this of your sample are reacting to that magnetic field when radio pulses are in there, right? And you're, instead of getting a graph from the FID data, you instead are winding up with you wind up with a picture of these different environments. Okay, so the great thing here, of course, is that compared to other radio imaging techniques, usually that involve radioactive isotopes, things that involve radiation that's a little bit more harmful, and therefore you're kind of limited in how much data you can collect at a given time because you don't want to expose the patient to a lot of radiation. Here with MRI, you're dealing with a magnetic field and radio pulses, which, remember, radio waves are all the way at the lower energy end of the electromagnetic spectrum, right? So definitely not harmful stuff, right? So you can run MRIs and get like tons of data, and get very useful data in that respect. So here are a couple of slides I've actually stolen from my Chem 103 lecture. We do a chapter on radiochemistry, and part of that chapter talks about radiomedicine. So I do talk a little bit about MRI there. But I kind of highlight how it's kind of neat for doing things that you can't really do with a lot of other techniques, because you can take so many pictures. Effectively, you can take images of something that's moving and make, well, a movie out of it. So So here you can see we've got an MR scan of a heart and lungs, um, but you can get essentially a movie of this heart beating, right? So you can look at it beating and look for anomalies that way, okay, as opposed to uh, let's say a CAT scan where you're getting like just a still image of it, which again can be useful, but sometimes you need to see the movement to see if there's something wrong with it. Or, the old fashioned way of using a stethoscope where you're trying to identify problems by sound and you're kind of limited in terms of your diagnostic ability there. Okay. The other image I showed my Chem 103 students is this one, which I think is a really cool picture, where we have, you can get people to perform different movements. In this case, speech. So you have two people talking in different languages, and you can actually see the difference in their speech patterns or the way they form their words. Um, and yeah, that's something you can't really observe with any other sort of medical diagnostic techniques, which I think is kind of neat. Okay. Um, all right, so that brings us to the end of this chapter, and let's go through a couple of practice problems with this. Okay. So for this first one, basically it's just asking why we use deuterated solvent. Um, Again, we use deuterium typically because it doesn't show up while protons do. You don't want your solvent interfering with your NMR spectrum. So since your solvent makes up the majority of your sample, you definitely don't want a lot of protons from your solvent showing up on in your data, because it would kind of drown out the signal from everything from your actual molecule that you're trying to study. In the case of carbon 13, of course, it doesn't really matter because you're looking at carbon, not hydrogen. So whether you use hydrogen or deuterium for hydrogens, of course, doesn't really affect things. All right, so here's an example of a molecule. Go ahead and see if you can identify, which types of protons you got. In other words, just first of all, ask yourself, how many signals am I going to see here? Which protons are going to sort of give rise to only one signal because they're homotopic or enantiotopic? Okay, so hopefully you've drawn that out. Here's that molecule again with all of the protons drawn out, so you can examine that a little bit. So, of course, all of your methyl protons are going to be equivalent to each other, and they're all homotopic to each other, right? So all of these three protons over here on this methyl group are homotopic to each other. These three are homotopic to each other. These three are homotopic to each other. All of your other protons will give rise to individual signals. Now, hydrogens D and E are not equivalent to each other, right? So they're going to be diastereotopic, not enantiotopic. And the reason, of course, for that is that we have this chiral center right next to it here. And so these two hydrogens are not in the same environment. One of them will be closer to that chlorine, one of them will be further away from it. All right, let's try and do this for from a more holistic approach. So we've got this molecule here. Go ahead and identify all of the signals you'd expect to see, predict their chemical shift, their integrals, their splitting patterns. Okay, so here's the answer for that. So when we draw out our our hydrogens, again, this methyl group here will have identical hydrogens. Okay, so this will give rise to a peak with three signals. With three hydrogens. Okay, so that's this singlet you see over here. Okay, it's connected to an oxygen, right? So it gets shifted pretty far downfield. About 2.5 ppm further downfield than you would expect for a methyl group. So a methyl group is normally typically somewhere in that around 1 ppm. So it is instead you see somewhere around between 3 and 4 ppm. Okay. Hydrogen B is those both of these hydrogens are equivalent. Okay, you can kind of picture that this ring forms a sort of a plane. If you're wondering about this carbon and this hydrogen, this oxygen not being identical, and therefore this molecule isn't completely flat, keep in mind that this can undergo some sort of ring flipping, so that kind of evens out this molecule and makes it kind of more symmetrical. Okay, so these two hydrogens are equivalent to each other. You also have a rotational axis going this way, so these two hydrogens here are equivalent to these two hydrogens here. Okay, so that's why you have an integral of 4 for hydrogen B. Okay, now hydrogen B is split into a into a doublet by hydrogen C. Okay, uh, but hydrogen uh, and hydrogen C is split into a triplet by the pair of hydrogen B's here. Okay, uh, it you might be thinking to yourself, wait a minute, aren't there 4 hydrogen Bs? Why don't I see a quintet? This one's a little bit tougher to realize this, but let's pick one of our hydrogen Cs here. And you can see that hydrogen C is within 3 bonds of these 2 hydrogen Bs, but not within 3 bonds of these 2 hydrogen Bs. So you've got to consider that it's only the 2 that are near it that split that one. But the integral gets increased to 2 because this hydrogen C, which is split by these 2 hydrogens, also gives rise to the same signal. Okay, and same thing for hydrogen B. It gets split into a doublet. So these 2 hydrogens get split into a doublet by this hydrogen C, but not that one. And likewise, these 2 hydrogen Bs here get split into a doublet by this hydrogen C, not that one. But they have the same signal as these 2 hydrogens, and that's why we have an integral of 4. Okay. Now, while hydrogen C splits hydrogen B into doublets, so does hydrogen D. So that's why you see a doublet of doublets there. Okay. Depending on what the coupling constants are, it might be a multiplet, but you'll probably see a doublet of doublets. And then finally, we've got hydrogen D. Now, hydrogen D is close to all 4 of hydrogen B, and that's why it gets split into a quintet, okay, with an integral of 1. In terms of the chemical shifts for all of these, hydrogen C is pretty far downfield because of it's being it's attached to this alkene. Hydrogen D is decently downfield as well due to its close proximity to that oxygen. Okay, same molecule, but this time we're going to look at its carbon-13 spectrum. So ask yourself, where will all the peaks show up for our carbons here? Okay, so we've got 6 carbons. Though due to symmetry, we're going to have some equivalency here. So ask yourself, how many signals would we see, and where would those signals be? Okay, so as you can see here, you've got basically this carbon and this carbon are identical here. If you imagine a plane going through your molecule here, since you can rotate around this carbon-oxygen bond, this carbon could be rotated to being in the plane. All right, so these 2 carbons are identical, and these 2 carbons over here are identical as well. In terms of where they show up, carbon 3 are just your regular sp3 hybridized carbons, just connected to other carbons, so they show up in that 0 to 50 range. Carbons 1 and 2 are also sp3 hybridized carbons, but they're connected by single bonds to oxygen, so that's why they show up in that 50 to 100 range. And of course, the carbon 4 over here are sp2 hybridized carbons, so they show up in that 100 to 150 range. Okay, and then of course, remember with depth 90 and depth 135, some of your signals either disappear or are changed. Okay, so in the case of depth 90, remember it's only methine carbons that show up. So the only thing that shows up for depth 90 are your it's basically carbon 2 and then your carbon 4s, which have 1 hydrogen coming off of them. Okay, everything else kind of disappears. With depth 135, everything except you know except a quaternary carbon will show up. The But the only difference though is any methylene carbons like C3 would have a negative signal. The peak would be pointing downwards. And that's it for this chapter. As always, please do try the practice problems that I've recommended. And check your work in the solutions manual. I've pointed out like how procedural this stuff is, and it's definitely one of those things that comes with practice. So please do take the time to practice this. And of course, as always, if you get stuck, let me know if you have any questions. And yeah, good luck with your quiz.